in the previous sessions, we already started this course. This is the 4th week now. We started with the constructing element stiffness matrices for spring element. Then we discussed when from spring assemblages, we moved on to discuss truss assemblies. And today, we will be looking at another element type. We will be looking at beams, how the stiffness matrix can be developed for beam using simple beam theory, as well as Euler-Bernoulli beam theory. We will be using certain theoretical aspects which you have already learned to derive the element stiffness matrices for beams. So at the onset, I would like to mention the concept is quite the same as it was used for a spring element when you're deriving a spring element and a truss element. So okay, the derivation might slightly differ based on the applied theories, but the concept, once you derive the element stiffness matrices, and when if you are to analyze a structure made out of, let's say, beams, then it is the same principle that you learned in the previous chapters. That is, you first construct the element stiffness matrices, then you develop the global stiffness matrices, apply the boundary conditions, and solve for the unknowns or the required, let's say, apply the compatibility conditions, and you need you can access the reaction forces, or depending on the problem, you can access what are the required parameters. So it is the same concept. So because it is the same concept, I will not devote a lot of time. I will quickly browse through these sections so that you can work, most of the things which I teach here in this course is best learned when you do it by yourself. And I will just giving you certain guidelines, and I will be directing you. And it's really important to take some time on your own to write these equations and try to grasp the concept. Once you grasp the concept, then you can use this concept without, of course, since you already know the background. So I will, as I mentioned, I will run through this section quickly because it is the same concept that you will be applying here, but the element or the problem in concern is different because we have now moved from springs to trusses, and in this case we will be talking about beams. I will just give out some time, especially on the derivation part, just for you to get a feeling for this, what is really how these beam stiffness matrices are constructed. Within this section, we will be first developing the element stiffness matrices for a beam using principles developed for simple beam theory. So you will have to, I will not go into details because you can recollect, and you can go through the references and access the relevant derivations. I will simply use them here so that you know what is really behind this concept in this course. So, and then we will be, as usual, we will move on to analyze beam assembly, and also let's discuss. So all this time we were discussing about point loads. So within this section, let's try to be more realistic and try to see how we can tackle if a distributed load is applied on a beam element. So it is so it is important to understand what is the difference between, let's say, what is a beam and why we need to consider it. What are the aspects which we will consider in this case, which we did not consider when we discussed spring and truss elements. So in order to understand, let's try to get the concept as to what a beam is. I have here given the definition. I have here mentioned the definition of a beam. So beam is a long, slender structural member which is subjected to transverse loading. So it means it shows significant bending effects rather than twisting and axial effects. Yeah. So what are the significant effects here? Are the bending effects. So whenever there's bending, what are the corresponding, let's say, physical parameters which we can use to characterize this bending? This is the bending moment and the rotation, isn't it? So so why we consider these elements are because these are really applied, or they are quite prominent in many applications such as buildings, towers, and many other structures. You must have seen beam assemblies. These beam assemblies are able to withstand transverse loading, and and it shows transverse displacements as well as rotations. So this is the motivation behind as to why we need to study this beam element. So to get an idea, let's look at a beam element. Here I have shown a beam element which has already undergone some form of deformation. So the purple color shows the beam element, and as previously, we can define local coordinate system. Of course, in the x direction, we have the x hat local coordinate direction. And of course, in the transverse direction, that is in the y direction, we can mention the coordinate system as y hat. Yeah, for the time being, we can mention it as y hat. So x hat and y hat are local coordinate system which we define, and the purple color shows the deformed beam. So this beam, which has an initial length of L, has undergone a certain deformations due to certain, let's say, certain applied load. So what are the two deformations that we have considered in this case? Let's say it has yeah. So if we apply the forces and the moments and the deformations which takes place at these two nodes, if we consider node 1, you can see that the force applied in the transverse direction, that is in the perpendicular direction, is, we can mention it as F1y hat, and the corresponding displacement is D1y hat. So this is nothing but the shear force acting at node 1. Okay, what else? Whenever this beam is subjected to loading, there is bending moment taking place. So we say the bending moment at M1 is M1 hat, and we can denote it using a curved arrow. And of course, the rotation due to the bending moment, the node will be subjected to a certain amount of rotation, and which we can denote by phi 1. Of course, with the hat sign. Similarly, at node 2, also you can define the shear forces and the corresponding transverse displacements given by D2y hat, and the bending moment as well as the twisting angle at node 2. Here it is important to note that we have omitted the axial effects, that the axial deformations, and we assume that this the bar is more subjected to, let's say, transverse displacement than axial displacements. So when we consider this beam element, there's a sign convention that we need to follow. Okay, what is this sign convention? This is nothing new. You are already familiar with this. Of course, during the second year courses, you have taken courses in solid mechanics and even in strength of materials, you have covered these aspects, hopefully. So let's get familiarized with the sign convention. So what are the boundary conditions, or let's say what are the physical parameters which we use to define this, the deformation as well as the forces acting on the beam? These are the parameters. Yeah. So if we consider the moments, we consider the moments to be positive in the counterclockwise direction. So the moments in the counterclockwise directions are considered to be positive. Rotations are positive again in the counterclockwise direction. So if the rotations are in the direction of the bending moment, then they are considered as positive. Forces are positive in the positive y direction. That is, here in this case, the two transverse forces, shear forces, are considered to be positive because they're acting on in the positive y direction. And of course, the corresponding displacements acting in the positive y direction are considered to be positive. This is the simple sign convention that you need to keep in your mind. So having that in the mind, let's try to develop the element beam stiffness matrix. And for this, we will first use the findings by Euler and Bernoulli, which is defined using Euler and Bernoulli beam theory, that for the moment, let's assume that the axial forces, the axial deformations, also let's neglect the axial deformations. Of course, throughout this section, we will be neglecting the axial deformations. At first, initially consider a simple case. So we will be applying this differential equation to describe this elementary, let's say, linear elastic behavior of a so-called, let's say, of a small beam element or part of a beam. And we consider the plane, let's say, in this case, you see, you can see clearly a figure. This figure shows a typical beam which has been subjected to distributed load in this case. You will learn this concept today as we move on, so don't worry about that. And within this beam, we have considered an elemental part defined by ACBD. And you can see the local coordinate system mentioned here. And once this is deformed, this beam gets deformed, this elemental part will also get deformed. We consider, so you can see when the elemental parts get deformed, this axis, let's say the principal axis along the length of the bar will also deform or also rotate. In this case, let's assume that it has rotated this plane. So I have drawn a perpendicular plane. So in this case, if I draw perpendicular to the AC plane, I can show it like what I have just drawn here. And when it is subjected to deformation, this perpendicular plane, let's assume, has rotated by theta degrees. Yeah. So in this case, we assume that the sections, let's say, perpendicular to the longitudinal axis of the beam, before bending and after bending, it remains perpendicular to the longitudinal axis. So this perpendicular, the plane will remain perpendicular. So if we define this axis, the centroidal axis, and the corresponding plane will always be perpendicular even after deformation. This is the assumption that we make when we derive this, when we use this theory. But in reality, when there are complex, let's say, deformations taking place, we can further introduce that this axis, the centroidal axis, will not be perpendicular to the deformed plane. So using that assumption also, we can further complicate this problem. So before we move on to the complicated problem or even discuss this complicated problem, we will first simplify this problem by using this Euler-Bernoulli theory, meaning that before, just the thing you need to remember in mind is the centroidal axis of the beam of the element you concern remains perpendicular to the plane before and after the bending has taken place. So based in this concept, this theory has been derived. And to analyze this, let's consider a small differential beam element. Yeah? Let's consider this beam element I have shown here. And try to apply the physical, let's say, forces. So this, you can consider this portion to be, let's say, A, B, C, D. Let's consider 2 points in this elemental differential beam. We can denote it using 1 and number 2. And let's apply the forces acting and the moments acting on these elements. You know, you can simply define the shear forces acting on node 1 and node 2. So V defines the shear forces. So at node 1, let's assume a V shear force is acting, and in node 2, let's define it as V plus dV, and we can just mention it, denote it in this manner. So the normal, okay, the distributed load applied on the beam elemental part is given by Wx hat. So it is a function of x hat. It depends on the length. Whenever the length is larger, the applied force will be larger. And what else do we have? We have the bending moment acting at node 1, and when at node 2, the bending moment will be m plus dm. So keeping these notations in the mind, we can simply analyze for force equilibrium as well as moment equilibrium around this differential element part. Considering the force element, a force equilibrium, what can we say? We can say the forces acting on, let's say, in the y direction, of course, to satisfy the equilibrium conditions, the summation of the forces acting in y direction should be 0. So what are the forces acting in y direction? There's plus V force, the shear force acting in the positive y direction, and in the negative y direction, V plus dV force, which acts in the negative y direction. And what are the other forces? The force contribution due to the applied distributed load is given by Wx times dx, because dx is the length of the element. So this is the total force applied on this element, and it is acting in the negative y direction. So by solving this equation 1a, you would be able to get a relationship for W, which is given by minus dV and dx hat, minus dV by dx hat. So it is a function of the shear force, let's say derivative of the shear force along the x direction, but in the negative y direction. You can define W using this, you can obtain W using these equations. So the second physical, let's say, phenomena that we have to take into account is the moment equilibrium. So the moment around, let's say, in this case, at any point, it should be 0. So let's take the moment around point 2 should be 0. And what are the forces acting? So minus V times dx. Why it is minus? So the shear force times the dx value here. Use the color. The shear force times dx value. Negative because it is acting in the anti-clockwise direction. dm, it is in the positive, let's say, clockwise direction. And of course, the m, the corresponding m contributions gets cancelled off, so I have not mentioned here. and the moment due to the distributed load applied. So Wx times dx gives the distributed load, and the corresponding distance is dx hat minus divided by 2. We take the half length of this element, and since it is in the positive direction, let's say counterclockwise direction, when you consider node 2, it is considered to be positive. So you take the moment equilibrium. Once you take this, once you get this equation, and you divide it by, let's say, take the divided by dx hat. So simply taking the derivative of this equation by dx hat, and of course apply the limitation that dx hat approaches to 0. Why? Because we are now considering a small element in the real case, or we in this instance we assume that we want the length of the element to be small as possible, so we analyze the limit where dx hat tends to go to 0. So with a bit of a simplification, you will realize that when the dx hat approaches 0, the corresponding, let's say, this term, because the w term, wx hat term, has to be multiplied by a value which is very close to 0, so this term will can be neglected. What you would end up is getting a relationship between the shear force and the bending moment applied at this elemental component. So now it's really convenient that you have a relationship for the distributed load in terms of the shear force acting along the beam, and you have also a relationship for shear force with respect to the bending moment applied along the beam, or in this case applied at different nodes. So you have interconnection between the different let's say physical parameters. So we can keep these two derivations for the moment aside and try to apply let's say Euler-Bernoulli beam theory, just to get access to differential equations to characterize this deformation, transverse deformation of this element. Yeah, so I will not be going giving you all the details, because the main this is a finite element course, and you can refer if the derivations are not clear, you can refer different reference materials, especially strength of materials and analyzing structures. Maybe you have already learned. Also, you can refer your lecture notes and see how these concepts were derived. So within this course, I will keep the focus towards the finite element concepts, and of course I show these derivations for you to understand the concepts behind them. So just try it on your own. Once you understand the concepts, you don't have to really worry about how these things are derived, and what are the really how this I mean, what I'm trying to say is these things will not be tested, of course, in the exams, but these things are really essential when you're analyzing engineering problems as engineers, because you really know the concept as to how these theories have been derived, and what is the basis of deriving the element stiffness matrices for a beam element. Okay, having said that, we are now at a junction that we have already obtained a relationship for the load, distributed load, in terms of the shear force acting along the bar, as well as the relationship between the shear force as well as bending moment. Now, let's try to consider this deformation which takes place in this bar. For this, let's try to find the curvature, curvature of the beam, which is given by capital K. So I will directly use this equation. The curvature can be written using the radius of the curvature. So here you can see the initial beam, the axis of the initial beam, and this shows the beam locations or points along the beam after the deformations. So along the beam, that is at a x hat direction, the transverse displacement is taken as is described by this function v hat x. W x hat defines the normal force or the distributed load applied along the beam. And at this specific location, if you consider a point here on the deformed beam and the original location of the beam, this is the original location of the beam, and this is a point along the deformed beam at a x hat direction. I'm discussing now along the direction of the beam, along the x hat direction. Let's say in x hat direction, we can assume a transverse displacement function along the y direction to be v hat. This is convenient because we have already used x hat to define the transverse displacement, so that we keep the parameters as low as possible. And at that specific location, the beam, the centroidal axis of the beam has rotated by psi hat, and the radius of the curvature of the beam can be given by, let's define it to be rho. So we can couple all these parameters, and the curvature of the beam can be defined by 1 over rho. Yeah, I will not go into details, but you can check this up on your own. This is the inverse, this is the definition which I have directly used here. An inverse of the radius of the curvature, which is equal to m divided by EI, where m is the bending moment and E is the modulus of elasticity of the beam, and I, of course, is the principal moment of inertia around the z axis, which is in the orthogonal direction or the perpendicular direction to x hat and y hat, the plane defined by x hat and y hat. So it is the perpendicular, the third direction, orthogonal plane, which is perpendicular to x and y hat plane. So we can define, based on these definitions, we can write an equation to access the angle, deformed angle, which is given by this equation, that is x hat is equal to, let's say, for small angle conditions, we can say it is dv hat divided by dx. So using this figure, you can clearly see that if the psi angle is let's say small, we can assume tan theta to be approximately close to theta. So you can obtain the tan theta value using, let's say, dv hat divided by dx hat. So using the small angle approximation, you can obtain this this expression. So and we assume, let's say, you have to take this into account, that the radius, the curvature of the beam is given by this definition, that the curvature for small slopes, if the slopes is small, you can define it by using this using this equation, the derivative of the transverse displacements with in the x hat direction. And of course, you can define for this small angles, the radius of curvature can be defined using the first derivative, the second derivative of the transverse displacement. Yeah. So using this curvature equation, which is defined by the transverse displacement, the second derivative of the transverse displacement in the x hat direction, you can substitute this value you obtain at this 1e equation to this equation here. What you would end up is getting a relationship between the transverse displacement as well as bending moment, modulus of elasticity, and the principle of moment of inertia along the z direction. So since you have a relationship now for this, let's say given by 1f, so I will just go through this. You can actually try this on your own and raise questions if you have. Once this once this definition is given by, let's say, 1f, you can substitute this back into the equations which we derived, given by 1c and 1b, 1c and 1b, which is this equation where the distributed force, normal distributed load is related to shear force, and what is 1c, that is force acting along the direction with which is defined by the moment of, let's say, inertia. Yeah, you can use this set of equations and so here and obtain an equation, let's say the relationship for v hat here. What you would end up it getting a differential equation given by this equation, of course, 1g. So I have done nothing new. I have simply used the equation 1c and 1b and substitute the bending moment. So I have found the bending moment value using this equation. Let me show you. So I have found the bending moment value using 1f equation, and you substitute this bending moment value here in this 1c equation. Then you have to get the derivative for this bending moment, where you would end up getting the shear forces, and that is what I have done here. So it's just substituting equations. You can just check if it's not clear. Just after the lecture, you can check it on your own as to how I arrived at this point. So you get a clean equation relating the physical parameters of the beam, the transverse displacements, the normal forces applied. So of course, let's say we can consider in this case that the modulus of elasticity and the moment of inertia, bending moment of inertia along the centroidal axis in the z direction remains constant. So we can take these two components outside of this equation, and we can assume that the applied forces, of course, in the normal distributed forces also to be 0. So what you would end up is getting, let's say, a neat equation, let's say fourth order differential equation, which derives the characteristics of a deformed beam. So using these principles or these concepts, let's try to go through the several steps which we already, the 7 steps, if you can remember, to obtain the element stiffness matrix for a beam element. So up to now we have done nothing. Let's say we have already laid the foundation for deriving the element stiffness matrix for beam.